process. And we have done the 0th step. We're doing the example of making 800 million pounds per year of vinyl chloride. And first step was to figure out if it's going to be a continuous or a batch process. And in this case, it was very clear that it was going to be a continuous process. And then we researched literature and we found several ways to make vinyl chloride. And we're summarizing different ways we found. Didn't completely finish that, but we have the following ways for making vinyl chloride. First one was direct chlorination of ethylene which was the reaction ethylene plus chlorine giving us vinyl chloride plus hydrochloric acid. And this does happen in terms of characteristics. I'll write here some characteristics. I'll try to keep them here. So this happens at low temperature and pressure. That's good. But high yield of highly toxic ethylene dichloride. Okay? Sorry, dichloride. The second one was hydrochlorination of acetylene. And then this one was acetylene with its triple bond. It's broken into a double bond with HCl to give us vinyl chloride. This has low conversion, high conversion, good, excellent conversion, 98% conversion. At not too bad conditions, 150 degrees C, and 1 atmosphere, using mercuric chloride impregnated on activated carbon.
You say that there's high yield of that stuff, but why don't you put it in the reaction?
Say again?
Why is it not on the right side of the reaction if it's produced?
This byproduct.
So you never put byproduct in?
Well, we're doing what we need for this, okay? For your project, you will need to put all byproducts, yes. So good point, Juan. For your project, you also have to add side reactions. Absolutely, you have to add side reactions. But for this one here, guys, I can't spend 10 lectures on this, so I have the essentials. But, so we also need, okay, we have mercuric chloride, inactivated carbon as the catalyst. And the part here is that you have huge amounts of acetylene. C is a two-step process. And let me write it this way. Dichloroethane from ethylene followed by thermocracking. Okay, I'm writing too small, but this room is not as deep. Okay, I will try to not go any smaller. Maybe I can put some lines to distinguish which. So, two reactions here. First, we react ethylene with chlorine, breaking the double bond and making dichloroethane. And the difference here is that this happens with a Friedel-Crafts catalyst at different conditions from this. Same reactions as here, but different catalyst, different conditions, different products. Okay? So this one is happening at 90, this has 98% conversion also, at 90 degrees C, 1 atmosphere, Friedel-Crafts catalyst. And the second step is the cracking of the dichloroethane. This is high temperature pressure, and this cracks into vinyl chlorides plus HC. And that has in the order of 60 to 65% conversion. At, what a beautiful ad. No one can read this. All right. So this is at 500 degrees C. It's 26 atmospheres. 26. Next one is a similar one, but it makes the dichloroethane differently. The dichloroethane from oxychlorination of ethylene, then cracking. I believe that's the last one I wrote last time. So this one is, the first reaction is ethylene plus 2HCl plus 1 half oxygen that can come from air, giving us the dichloroethane plus water. And this one is pretty good, not as good as this one. It's only 95% conversion, and that's significant. What is not converted here 2%, here 5%. So you can't think 95 and 98 exactly the same, but it's still a very good conversion. And this is at 250 degrees C, don't see the pressure. I'm assuming the pressure is close to atmospheric, but since I don't see it, I'm not putting it. And step 2 is the same as above, so I'm not going to write it again. At the condition, just write the reaction. So let's say you found those from literature. One thing you can look at, if there is any way you can combine other concepts to come with new concepts that can perhaps be promising. And one thing you'll observe here is that this step the cracking produces HCl from here, and this one, oh, yeah, okay. Oh, I didn't write the net reaction. I should have written the net reactions also. Let me also write the net reaction. So you have more than one. It's a good idea to also write the net reaction. So the net reaction here would be what? And I want to write the net reaction also here. So sorry for that. And I'll try to squeeze it here. And I'll squeeze it. So squeezing it here, the net reaction of this cancels out. And the net reaction here is, I'll put here an N for net, is ethylene. Okay? Plus chlorine, giving us vinyl chloride. It's supposed to be a 3. Plus HCl. The net reaction of this is the same as the first one. Okay? And the net reaction of this is ethylene. Now I have plus 2 HCl here, but I have plus 1 HCl here. So the net is plus 1 HCl plus oxygen from air gives us, this is what continues, vinyl chloride plus water. So I want us to focus a little bit on the net reactions of C and D. This net reaction uses chlorine and you get HCl as product. This net reaction uses HCl and you get more vinyl chloride. Any ideas of maybe something we can do to have a more efficient process?
What do you mean by more efficient?
Okay.
What do you mean by more efficient?
Okay, so one idea is separate that HCl and use this process also, right? Combine those two. It would require a lot more hardware. You'll be running 2 processes in parallel. So it has significant cost with it. But if, let's say, the cost of chlorine and HCl is high, it might be advantageous. So always look if by combining other concepts you can come up with new ideas. So I will write that the last one. So the title of your text gives is balanced process. For chlorination of ethylene. So basically, what we're talking about here is using ethylene with chlorine to make dichloroethane using also ethylene balanced with HCl. To make more dichloroethylene plus water. And then we have dichloroethylene from here, we have dichloroethylene from here, so we have two dichloroethylenes. So take the two dichloroethylenes and crack them to get two vinyl chlorides plus two HCl's. And what is the net reaction of this one? So the net reaction of this one is two ethylenes. What happens with chlorine? Plus chlorine, okay, plus one chlorine. And what do we have on the left-hand side? We have two HCl here, but we have two HCl as product here, right? So no HCl in the net reaction, and we plus one of the oxygen. Okay, my Cl looks a little bit like an O, so Cl2 plus 1/2 oxygen, and this will give me two vinyl chlorides. Plus one water. Okay, I better stop. See that way, right? Yes. Which would be equivalent to one ethylene plus half a chlorine plus quarter oxygen, giving us one vinyl chloride. So the advantage of this, over, for example, this one, here we need to use one chlorine to make one vinyl chloride. Here we have to use only half a chlorine to make one vinyl chloride. So if the cost of chlorine is high, clearly I would have an advantage that I need to use only half the chlorine that I need to use in scheme 2. In scheme 1, sorry. Or scheme C. Scheme C is the one. Okay, so we have come up with different candidate reactions. At this point, we want to proceed and select which one is the best to develop our design. Now, usually you have more than 5 candidates, you have a lot of candidates for your project. Next week, not today, but next week, I'll be counting how many reactions you have come up with. Now, different catalyst, if it results in different conversion and has different temperature and pressure, it's different reaction. In some cases, you will need to go forward, you will need to have conversion, which usually you'll find, or kinetic rates. Okay, this is an absolute must. And also, you need to have information to allow you to calculate your residence time, space time. Okay? Because that's how you scale reactors. To be able to size your reactor, you need to have the space time. You call it space time, right? No residence time most of the time? Mm-hmm. My days, you're always calling it residence time.
We call it tau.
So, you need that information, but even if you don't have that information, list it. As we'll discuss, you'll immediately throw them away, but at the beginning, list them to show me that you also found those reactions. So don't only list reactions that you'll be able to use in your project. List also reactions that you cannot use in your project. But anyway, so you have a whole bunch of reactions, and it would take too much time to try to do detailed designs for each one of them. etc. So you need to do something to cut the choices. And there are a couple of tools that are used, and they're used for designing a lot of things, not just that. If you do product design, again, you come with different concepts, and you have a lot of concepts. You need to select which is the most viable concept. And there is something called decision matrices. And we're going to be using two types. The first one is a very rough selection tool. And the first decision matrix is called a screening matrix. In a screening matrix, you create a matrix, and you have here major criteria. So here you put this column, will have major factors. You don't put any minor factors. And you put here your candidates. A, B, in our case we have 5 candidates. C, D, E. And usually what you do is you pick one of your candidates to be the basis of comparison. And you go through every criterion that you have. And let's say in a screening matrix, let's say I chose, for example, let's see the one that I chose here. Let's say I chose D as my comparison measure. So D would have, essentially you put S means comparison same, etc. So if I've chosen, I think I chose E, sorry, I'll change that. Let's say I chose E. Then E will have S, 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 S for all the criteria. And let's say one criterion is
cost.
Yeah, but okay, there's something we're going to talk about gross profit, but let's say one is selectivity and conversion, for example. Don't write that down, I'm going to change what I'm writing here. So don't write this, just say something that we have. Okay? So you would look at the criteria, at what you have here, and then you would be comparing each one of them. If it's about the same, you will put an S. If it's better, you will put a plus. If it's worse, you put a minus. And then you add all the pluses, the minus, S being 0, and you decide certain number of alternatives for further investigation. So if you come up with 35 different reactions, okay, you will have a matrix of 35, and you will have only a few major criteria, and plus minus S's, and you'll select maybe 5 to 8 for further investigation. So you go down that way from 35 to, let's say, 7. You follow me? And then there is the scoring matrix, which is a more precise tool, needing more information, and we'll work with that. Now, for your project, screening matrix will have one very important criteria. Can model in unison. If that one is a no, don't even fill anything else. I'll put for that a minus with a circle. That means I don't care what the other things are doing, I can't choose them. Okay? So, to be able to choose something for forward investigation, you need to have conversion or kinetic rate, and you have means for calculating spacetime. Either given spacetime, but if you have, for example, a lab experiment, and the lab experiment gives you the flow rate and the volume of the reactor used, you can calculate the spacetime, and therefore you have it. But if it just gives you the reaction without any information whatsoever, you list it, you get credit for having it among the 35 that you reported, but you stop at the screening rate. Now, the number one criterion always, when we're talking about a chemical process, is, and now how you can write it, is something called the gross profit analysis. What that means. The gross profit analysis simply takes the best you could possibly do in terms of profit. It ignores any cost of separation. It assumes that your separations can be perfect. And with recycling, separation recycling, it assumes conversion. Separation. It assumes conversion can be perfect. Because with separation recycling, you can get effective 100% conversion if you have 100% selectivity. You have to consider side reactions. Okay? But what you do is you write the net balance that you have of the main reaction and of every side reaction. And you calculate the value of all the products minus the value of all reactants. And because you have different reactants, etc., you standardize the comparison on the product. So you calculate, for example, how much is the value of the products minus the value of the reactants per, let's say, mole of vinyl chloride that I made. If that this is called the gross profit, and I'll do an example in a second. Or maybe next time if we don't have time. If that value is negative, I can stop. If your reactants are more valuable than your product, obviously you're not going to make any money out of that. Okay? So that's the very first thing you'll be calculating is the gross profit analysis. Quick question. Go ahead.
I was just wondering if there was like literature we can look at or something.
Your book.
Okay.
This is material from your book. Any edition. Okay. So we are going to do the gross profit analysis for each of these. We're not considering any side reactions. The side reactions can also add some gross profit if you make a byproduct that's valuable, okay? So you could have some value there. But in this case, let's simplify it and just calculate for each one with the net stoichiometry what is the gross profit. I will take the values from your text, and so let's see, 6:48, I have 7 minutes. Okay, let's go on Excel. We're going to do it on Excel. We're going to have the values given. I will be done by 7 o'clock. We have the thing, so maybe not by 6:55. If I'm not done, we will be. Friday we're continuing high units, okay? So let's calculate gross profit for all the reactions that we have. So first of all, I'm going to list all the components for which are involved. So ethylene, of course, for reactions. Acetylene, in oh, sorry for that.
Oh, it's
Ethylene, acetylene, chlorine, HCl, and of course our product, vinyl chloride, water, byproduct, and oxygen, I'll put parentheses, and I will give the values by your text, and normally you get values per weight, not per mole. So you cents per pound, and the value that your text has, it has 18 cents per pound for ethylene, 50 for acetylene, 11 for chlorine, 18 for HCl, 22 for a product, vinyl chloride, and water,
0.
close to 0, and air, practically 0, yeah, 0. But our reactions, our stoichiometry, is in moles. So to do the gross profit, we have to first go to moles. So one thing we need to translate is in cost per pound mole, and to do that I need to have the molecular weight. So here's the molecular weight of everything that I have. So 28.05 for ethylene, 26.04 for acetylene, 70.91 for chlorine, 36.46 for HCl, and 62.59 for vinyl chloride. Obviously, the other two are 0, I don't care. So how do I get? Be very careful not to divide instead of multiplying. What is bigger, pound or pound mole? Pound mole, right? So what we have to do is, to get the pound mole, the price, we multiply by the molecular weight. I've seen sometimes teams divide by molecular weight. Only healthy for your grade, I can tell you that.
You wrote it on the wrong.
Cents per mole. So we'll divide this equals multiply times the molecular weight, 504 cents, and copy down. And you know the shortcut, if you just double click when you get the right bottom crosshair. Okay? And to judge its reaction, we have to multiply by the stoichiometry. And we use the net stoichiometry that we have, the net reaction stoichiometry. So, for reaction A, candidate A, what is the net reaction that we have? It's 1 ethylene, so minus 1 for ethylene, plus 1 mole of chlorine, minus 1. It gives us 1 mole of vinyl chloride and 1 mole of AC. Okay? And how do we calculate the gross profit? Let's write down here what is the gross profit. And per pound mole, and then we'll have gross profit per pound. Per pound. So the gross profit per pound mole, we gain money for everything that is product. So the vinyl chloride will give us money. Also, potentially, will give us money the HCl. We could possibly sell it. So it's the sum of the product of this column, of every element of this column with an element of this column. You can do it in separate columns, but there is an Excel command. I believe it's product sum, or some product. I don't even know this. It's product sum, sum equals sum product parentheses and highlight the first column, comma, second column, close the parentheses, and 748.35 is the gross profit we would make from reaction A. Clear, everyone? Oh, I should have had it. I should have done it here.
Just drag it.
Well, it will change the equation. Faster if I didn't do it. And also you see the muscle again. Okay, for some product, open parenthesis, highlight, don't have highlighted to the zero, comma, highlight the A part, close parenthesis, that's it. And I really want it per pound, so how do I get it per pound?
Times molecular weight. Oh,
Now I'm going from pound all to pound, now I divide.
oh, you tricked me.
Okay. Okay, so here's gross profit per pound. Almost done. Alright, so that is equal simply above divided by the molecular weight of vinyl chloride. And I'll put the absolute address pressing F4 so I can copy the formula maybe. I don't know. So that's the gross profit for path A. Path B is the acetylene. Okay? So we make 11.96 cents per pound of vinyl chloride gross profit. Now that's an upper limit, okay? We're going to make a lot less. This doesn't take into account cost of separations, cost of equipment, etc. But if this number is negative, forget it. So let's do B. B has what? Acetylene, -1. It has
Class ended.
chlorine, -1.
They ended at 55, right?
Oh, no, that's HCl, sorry. HCl -1.
Class ended at 50.
What?
I think class, somebody was saying that class ended already.
Yeah, I will go ahead. I'll finish this one, then I'll finish. Thank you, Juan. Not really. Equals some product. Open parenthesis. Highlight the cents per pound, comma, and now highlight the B. And close that. Do we need to talk about acetylene anymore? No. Acetylene also because of its danger for explosion. We probably have a minus with a circle for that. Save that. We'll finish with this and we'll continue with the selection of the reaction Monday.